Presentation is about my survey paper on non-Fourier heat conduction equation. It all started with a question of having it going through, is it possible to have a thermal wave or a thermal shock in a solid? The problem is heat conduction is basically follows diffusion equation. So uh, it's having a shock or any kind of thermal wave solution is not allowed. At the same time, if you look at the Fourier heat conduction equation, it does have some problem. So it's based on thermodynamic equilibrium, and it assumes infinitely fast wave speed. But at the same time, we know that it's not realistic. And finite wave speed means possibility of having some kind of waveform. So we look at non-thermodynamic equilibrium, and that's what people did. So at some point, McNally presented a paper in 1970 uh, of capturing waveform of thermal conduction by comparing crystals with low purity and high purity. If you look at low purity crystal, it only shows longitudinal and transverse first sound peak, and then it turns directly to diffusive heat conduction regime. But when you use high purity crystal on top of longitudinal and transverse first sound, he began to see the appearance of another wave before turning into a diffusive regime. In the same year, Jackson published another paper by running the same or similar experiment that confirmed the existence of thermal wave-like phenomenon. And in another paper in the next year, I think he basically presented another paper with better signature of the incipient waveform. With that, he basically found connection between crystal purity and thermal conductivity. In his paper, he basically showed how he grew pure crystals, and whenever he goes through the next growth, it became purer and purer. So if you look at the thermal conductivity of the first growth crystal, it has somewhere between 50 and 60. And the fourth growth, the purest crystal he grew, its thermal conductivity is higher than 200. So they basically established the relationship between crystal purity and thermal conductivity. And with that, they looked at uh, the Boltzmann equation, which actually becomes using the momentum conserving and non-conserving equations, uh, this kind of form, where n represent phonon distribution function and tau represent relaxation time. Tau n is for n process. Tau r is all the processes that has resistive sort of nature. And the solution to this equation, to this form of Boltzmann's equation, really gives thermal conductivity in terms of the first term, K1, it's basically as a phonon, as a functional phonon with tau C, which is represented as 1 of tau C is 1 of tau N plus 1 of tau R, sort of effective relaxation time. And K2, which has slightly complicated form. Note that the first K1 is it's a function of tau C only, whereas K2 is really it has more complicated form, tau C of tau n divided by another term has tau C of tau n tau r. So what this means is that for pure crystal, where tau n is a lot smaller than tau r, K basically becomes mostly becomes K2. And for resistive crystal, where it's reversed, K becomes K1. So he there's another paper by Borman which actually compared K1, magnitude of K1 and K2. And you can see that within the temperature regime of 10 to 30, K2 dominates, which is related to the presence of thermal wave. So this page sort of summarizes various types of photon scattering, and there are like boundary scattering and dislocation scattering and U scattering and impurity scattering, and these are all momentum non-conserving. And there's normal scattering, which is momentum conserving. So, uh, except this normal scattering process, boundary dislocation and U process and impurity, they all fall into the resistive scattering. With that, we can actually start looking into non-equilibrium equilibrium thermodynamics, and we start from the fairly well-known equations. And with the assumption of the wavelength of n process a lot smaller than the wavelength of resistive processes, it turns into this type of form, which actually starts having the resemblance of second derivative in T, uh, second derivative of temperature in terms of time. So in the limit of the wavelength of a normal process approaching zero, this equation actually turns into this types of equation where we suddenly have a second derivative and in time and second derivative in space, which is well-known wave equation. So in the limit of the wavelength of resistive, oh, this is resistive process, sorry about that, a lot larger than one, the momentum equation here actually gives a solution shown in this equation. So based on the assumptions that we made, what it means is that to have wave-like solution in heat conduction equation, the wavelength of a normal process needs to be a lot smaller than the characteristic uh, length of the test article. And then wavelength of the resistor process needs to be a lot larger than the characteristic length of the test article. And at the same time, the pulse duration should be smaller than this value given here. So since wavelength is related to relaxation time, all these relaxation time of different phonon scattering do play a role in the formation of thermal wave. Kovacs basically simulated the behavior of the non-Fourier heat conduction equation, and he captured through simulation uh, the the test result fairly well. You can see that the red is the simulation result and black is the test result. He throughout different temperature, he does capture the general shape. Uh, and also for the second, the other paper from Kovac, Jackson, he also showed fairly promising uh, form of capturing the thermal wave here. Okay, another researcher, Bacteria, he basically applied similar type of non-Fourier heat conduction equation to nano-sized semiconductor. and he was able to compare the Fourier model and SPL model, which is another type of non-Fourier heat conduction model. He captured the difference, and uh, the the solution from the SPL model had better match with actual test data. Another researcher, Google, uh, he basically applied a similar non-Fourier type of heat conduction equation, and he applied that to capture the thermal stress. And again, he used this form of non-Fourier heat conduction and combined that to uh, stress formulation in non-dimensionalized form, if that's the final form of equation he used. And if you look at the left upper graph, it basically showed how uh, the wave solution changes as duration of heat burst becomes shorter and shorter. Uh, the blue curve shows the duration of heat burst comparable to relaxation time. We have slightly curvy solution. As the duration becomes fairly small, 2% of the original basically starts capturing very sharp wave-like solution. And if you look at the next graph, it's basically temperature at x equals 2L and shows how the temperature changes. Uh, the solid line represent non-Fourier type solution, and dotted line represent the Fourier type solution. So we compare the uh, blue solid and blue dotted line uh, at the push duration of 1 times the relaxation time. You can see that you can still see that the non-Fourier solution, which is CB, that's another type of non-Fourier heat conduction form. It it basically captures sort of wave-like solution, more like shock-like solution compared to Fourier type, which is really diffusive. And when he sort of shortened the heat flux duration, the which is red, the contrast become a lot sharper. So he was able to show the assumption of capturing thermal wave that the duration of heat pulse needs to be lower than the characteristic values. The other graphs on the bottom compares solutions of the non-Fourier type and Fourier type uh, of thermal stress. You can see that the solid one is a non-Fourier type and dotted line is Fourier type. So if you look at the blue uh, Fourier type and compare that to the blue non-Fourier type, you can see that non-Fourier type actually captures more dramatic value. And for red, it's actually even worse. Similar story here. Non-Fourier type uh, right. So if you look at non-Fourier type here, with the speed of the thermal wave, you can see that it actually captures a lot more dramatic effect at this speed of sound. Okay, another researcher called Huberman, he he basically runs experiment to capture thermal wave at higher temperature. Like if you look at the previous ones, the temperature range was somewhere between 10 to 30, but in his experiment, he ran the test at 85K, and then he was able to capture the wave-like uh, behavior uh, in the temperature variation. And applying Boltzmann transport equation, he was able to capture the similar behavior that's shown in his experiment. So, by spending some time on the existence of thermal wave and verifications, there have been many research papers and many research done already to show that it is a real phenomenon. And then by taking non-equilibrium thermodynamics approach, the non-Fourier heat conduction equation was capable of capturing second sound as thermal wave. So far, due to the assumptions made in deriving the non-Fourier heat conduction equation, its application is fairly limited. But at the same time, when it does, it is capable of capturing thermal wave that diffusive equation is not capable of. That's the conclusion that I came to. And then this page lists references used in this presentation. Thank you.